Hi, welcome to Real Learning Center. Today we are going to talk about Newton's third law, the most famous law of Newton. We'll see basically how it is related to Newton's first law and second law. Okay, and then we'll also understand what is this third law. We'll also know a little bit more about what are the misconceptions as associated with Newton's third law. So today what we will see is we have actually started from the causes of motion, first law, second law, and we also understood the second law in the context of the momentum. So now we are going to talk about the third law. The third law is the most famous of the Newton's laws, most probably because it is a rhyming law. Okay, so let us see how the Newton's third law is. Okay, why it comes from? Why is it important to state a third law after two laws? What are these two laws? First, we will see them. Okay, the first law. We know very well that everybody preserves his state of rest or of uniform motion unless compelled, impressed upon by an external force. So we said that this is the Newton's statement, and our simple way of talking about that is a lazy law. Okay, so that means things tend to be lazy. If you don't push them, they don't move. If they are moving, if you don't stop them, they don't stop. They don't change their direction. So these are the world, the universe basically has objects which are basically lazy. Okay, so that is what is the Newton's first law. Okay, that's a very nice insight, isn't it? And then we talked about when we don't put an external force, the law states that it doesn't change its state of rest or uniform motion. But when you put an external force, what happens? That is the question that is answered in the second law. Okay, in the second law, we talk about what happens when you put an external force. So Newton's second law says when an external force is exerted on the object, so it accelerates. Accelerates means changes its velocity. That means if it is at rest, it will start moving. If it is moving, it may change its direction or its velocity, speed, or it may change its, it may stop. So these things can happen. That's called acceleration. Okay, and then it is directly proportional to the force. This acceleration, how much it changes, is proportional to the force. That means more force, more changes. Less force, less changes. Okay. So and inversely proportional to the mass. If it has more mass, okay, it is hard to accelerate, change it. So it is natural in our real world that if something is actually having heavy mass, it is hard to turn it around. If it is heavy bus going in a down in an inclined plane, is very difficult to control than a lighter vehicle. Okay, so the mass, as the mass increases, the acceleration decreases. Means even if you put the same amount of force, acceleration will be less. So that is basically what our Newton's second law talked about. It also told us that the direction of acceleration actually is in the same direction of force. That means if we push like this, it cannot accelerate in a different direction. So these are the few things that first law and second law talked about. Now what is the third law going to talk about? So we also said that in the second law, A is equal to F by N, or F is equal to MA is the statement of the second law. So the question now comes is, why is the third law needed? So till now we were talking about, the first we talked about when there is no external force. Then when we talked about when the external force is there, what happens to the body? The third we are talking about when the external force is there. Not only what happened to the body, what will happen to the one which applied the force? Okay, the body which applied the force, not the only body on which the force is applied. So if you are pushing the ball, okay, we know what happens to the ball. That is the Newton's second law. So the third law is to know what happens to you. So that is the question of third law. So if you push it, it goes. That we know. And our hand may simply stay there. It will not go anywhere. That is our experience, isn't it? Our hand stays there. But there is another experience too. See, if you are actually pushing a cart, okay, you may actually push along and go along the cart. You are pushing and you are also moving. These are the two observations that we have made. When we push something, okay, the body that we pushed goes and we stay. Okay. Second one is we pushed and we went along. Okay. That is our observation about the body which is pushing. Okay. Is that all? Is that the right observation? Is it how Newton observed? So let us see that. Whether Newton observed it differently than this. Okay, does he get anything more fundamental to this than our observation? So where do we go for this? So we are actually, it's a little bit harder to do this on the earth. Okay, on the earth you have the gravitational force, frictional force and all that. So it is better to go into space to really understand what happens when you push something. Okay, here I am standing in space and you can see that there is this astronaut who is actually holding a ball and he is going to push it now. And when he pushes the ball, what will happen? Let us see. Okay, push the ball. Surprise, isn't it? When he pushes the ball, it is not just the ball that went away, he also went back. That's a great surprise. We have not seen that here. Or is it? Have you seen it here? Think about it. When you push water in the swimming pool, trying to push the water back, you actually go front. So you push the water back and water pushes you to the front. So that experience is there even here. But this is a very nice experience to see. Now what is happening here? What is the Newton's third law saying about this? When astronaut pushes the ball will also push the astronaut at the same time with the same force. That is the beauty of the Newton's third law. It is happening not after he pushes the ball. Okay, not with a different force. It is the same at the same time when the astronaut pushes the ball pushes the astronaut at the same time, simultaneously and with the same force. So, this is the law of Newton, this third law of Newton. So, let's understand it a little more detail. So, what is happening here? Here is an astronaut and here is a ball. And when he pushes the ball, there is a force on the ball to move in this direction. That is the arrow that is showing you, force on the ball. And there is a force on the astronaut. It is pushing the astronaut backside. Okay, there is a force on the astronaut. We are saying that force on the astronaut is equal to force on the ball. So we call that as action and reaction. So one of the forces is called action. The other force is called reaction. So now but they are also in the opposite direction. You can see the word we use reaction is because they are in the opposite direction. One arrow is pointing this way, another arrow is pointing that way. So they are equal sized arrows pointing in opposite directions. So force on the astronaut is equal to the force on the ball and in opposite direction. So action and reactions are equal and opposite. Okay, that is what we are saying. That is what not we are saying. That is what Newton said. Okay, now, however, there seems to be some kind of a flaw in this. It occurs like that. So if that is the case, okay, do we see that the astronaut and ball, are they both going to move equally at equal speed and at equal acceleration? How do they move? So we have to see that. Okay, and then actually Newton says that though forces are equal, acceleration need not be equal. He says you have to go back to my second law. What does second law say? Second law says A is equal to F by M. So you can see very clearly here, force equal size. You can see that force and this force, both of them I have put equal. In the first one, astronaut is heavier, his mass is bigger. And in the ball, it is like smaller, M is smaller. So you can see very clearly that if the M is bigger in the denominator, A becomes small. And if M is smaller in the denominator, A becomes bigger. That means acceleration of the ball is bigger and acceleration of the astronaut is smaller. It shows in the small blue arrow. Astronaut is smaller and the ball goes with a higher acceleration. So you can actually watch this. Okay, I will replay the same thing and you can very clearly see the ball shoots off faster than the astronaut. Take a look. Okay, so both the forces are same, but accelerations are different. Very interesting indeed. So this is how the law actually states. Okay, definition of the Newton's third law. For every action, there is an equal and opposite reaction. Equal and opposite. That is the keyword. Okay, and action and reaction are not the keywords, because action and reaction you can replace them. If you call one of them action, other one you can call reaction. But you can call the other one action and this one as reaction. It doesn't matter. Okay, both are simultaneous. So for every action there is an equal and opposite reaction. For example, you see a book is on the table. Now when this is happening, there are forces at play. Okay, there is a force which is basically upwards on the book and the downwards on the table. So the book exerts a force downwards on the table and the table exerts a force upwards on the book. One of them we call reaction, other one we call action. The choice is yours. Okay, normal force of the table, I mean perpendicular to the table. Perpendicular surface is called normal. Normal force trying to put the table in the book up, and the downwards force of the gravitation which is pulling the book down. Think about it. Now if there was no normal force, then book would have fallen through the table to the ground. And that's not happened. So there is a normal force. Now, but one important thing you have to understand. You cannot say that these two forces are equal and opposite and hence the book is at rest. It's a wrong statement. The fact that book is at rest has got nothing to do with Newton's third law. At least directly it has got nothing to do with Newton's third law. Okay. These two forces, for reaction and action, they don't actually act on the same body. It's not, the reaction and action are not happening on the book. Reaction is happening on the book and action is happening on the table. So there are two different forces on two different objects. They happen to be same in terms of their value, equal and opposite. So that is the Newton's third law. So there are many misconceptions about the Newton's third law. Okay, because this is actually a very nice rhyme is there. For every action there is an equal and opposite reaction. People remember it. So if you ask anybody, even at the age of after passing matriculation and goes into college and then works for about 20 years, then you ask him, do you remember anything from Newton's laws? Yeah, they will say third law. Okay, but their interpretation of third law, which we remember, sometimes there is a lot of misconception. Okay, so let's see some of the interesting misconceptions about Newton's third law. The first one being, if you throw a ball, the ball will come back from the wall. So throwing is action and coming back is reaction. So this is something that you would have been given an example and thought about Newton's third law like that. But it is completely wrong. Okay, throwing is not the action and coming back is not the reaction. Okay, this is a wrong way of understanding Newton's third law. Newton's third law is acting here, but not in the way it is expressed. Let us see why. Okay. And second misconception is, people use this Newton's third law in a loose sense. Okay, the sense that if you hit somebody, they will hit you back. Okay, that is bad. So don't hit because of Newton's third law. So it is like a cause and effect in the real world in a very different way. Okay, this is a moral. It's a moral story, but this is not Newton's third law. Newton's third law is much more mathematical than this statement. Okay, and the third one is, action and reaction are equal and opposite, and hence they cancel each other. This is the most the biggest misconceptions of the Newton's third law. Most people believe like that because they are equal and opposite, they cancel. Please understand that they act on different bodies. They cannot cancel. If two forces act on the same body, they can cancel. I am pushing the wall here, okay, and you are pushing a motorbike there, opposite direction, equal. Do they cancel? They don't. So they cancel only if they act on the same body. If they are two different forces, they act on different bodies. They don't cancel. Okay. A body may be in movement, body may be in acceleration, body may be standstill. Anything can be happening when Newton's third law In all cases, Newton's third law is valid and working. Okay, and there is another misconception. This has happened because of the English. Okay, or maybe the original wordings. The Newton's third law talked about action and reaction, and we, in our day-to-day sense, we always think that reaction happens after action. Okay, so that is basically our way of understanding words action and reaction. But that is not the case here. Here, action and reaction happen simultaneously. They don't happen one after the other. So those words are somewhat missed now in the Newton's third law. Okay, and some people also think that action is the cause and reaction is the effect. Means first what causes is the action, and then what comes back after that is the reaction. That is wrong. There is nothing like cause and effect relationship between action and reaction. They happen simultaneously, they happen together, and with the same force, opposite direction. Okay? And lastly, okay, there is this philosophizing the concept of Newton's third law and saying that it is wrong. That is my high college days, people used to say that if you love someone, they may not love you back. Hence, Newton's third law is wrong. So this is for a joke. Okay. So let's go to the next step. So now, if you watch the recoil of the gun, you will actually see the Newton's third law. Just watch. When you fire a gun, how it recoils. Okay, so that is the recoil of the gun. The bullet goes forward and the gun comes back. You can see bullet goes forward for a very long distance, gun comes back for a very short distance. That's because their masses are different, though forces are same on both of them. Okay. So now let's see the important points of the Newton's third law. What are the important points that we need to remember in Newton's third law? The first and foremost thing is that words action and reaction give the impression that action comes first. Don't believe that. Okay, they happen simultaneously. This is not to be forgotten. And second one is that action and reaction do not cancel against each other because they are acting on different objects. Okay. And thirdly, action and reaction forces are equal, but it does not mean they produce equal acceleration. They don't mean that they produce equal acceleration. Wherever there is higher mass, it produces lesser acceleration. Where the lower mass produces more acceleration. So, if you remember all these 3 points of the Newton's third law, you will not remember it wrongly. Okay? It's a very interesting law. We'll see where this gets applied. For example, one simple scenario, let us take. There are some examples of third law. We can say a car moving, a rocket taking off, and you can also say spring. Okay, so where are the forces, action and reaction forces here? If you do a few of them, you will get an idea. So in the case of the car, you can see that the car actually pushes the road and the road pushes the car. Interesting. And here you can see the rocket. In the case of the rocket pushes the gas outside and those gases push the rocket up. It's like swimming. You push the water backside and water pushes you forward. Spring, you can see you are actually pushing the he's pulling the string and string is pulling him. So that is what is happening here. And you can very clearly see in this case of they both are at rest. Here they are all moving. One of them is accelerating. Anything can be happening. Okay, but everywhere two forces are acting. A few more examples you can see. Interesting examples. Helicopter. How does a helicopter go up? Helicopter actually blades. They push the air down and the air pushes the helicopter up. Okay, and a man kicks the ball and ball in turn kicks the man, so it gets painful to him. Okay, and you can see that a ball is dropped from the Tower of Pisa. So when the ball is attracting the earth is also getting attracted towards the ball. The forces are equal. So that is the beauty of Newton's third law. Both the forces are equal. But acceleration, of course, they are different. Now here is a simple question. We know that the earth pulls on the moon, and does it follow that the moon also pulls on the earth? That's the question. Think about it. So the answer to that is yes. Both pulls make up an action-reaction pair. Okay, it need not be pushing and pulling in terms of contact forces. Here gravitational forces are also like that. Earth is pulling the moon and moon is pulling the earth. Okay, and these action-reactions pair are responsible for the interaction between earth and moon and makes the moon go around the earth. It is not just the moon going around the earth, remember this. Okay, it is earth and moon. Both are going around what we call a center of mass of the both. So which we will discuss a little later, because earth also will be moving a little bit. Why so? We will see that later. Okay. And then another interesting question is, a car is accelerating along the road. Identify the forces that makes the car move. What makes the car move? You can say engine makes the car move. It is true. The fuel makes the car move. It is true. But really, what force makes it move? Let us see what force makes it move. Okay, I will say it is the road that pushes the car. Really? So only the road provides the horizontal force that pushes the car forward. How does it do that? So it is again using Newton's third law. So what happens is the rotating wheels actually push the road backward, and the reaction is road pushes the car forward. Now what happens is that the road is heavy. Heavy means earth. So on that the acceleration for that force is minimum, whereas the car is very light when compared to earth. So acceleration that makes it move. So that is how car moves. It is the earth that is pushing the car. And why is it pushing? There are two forces. One is the force that pushes the car, pushes basically the earth. The other force is equal and opposite, which pushes the car. So that is how the car moves. Isn't it interesting? So let's go back to our first question and our first observation of how when you are pushing the cart, what happens? Okay, when you are pushing the cart, there are two action and reaction pairs are here. One is you are pushing the cart and the cart is pushing you back. So the two forces here. One force acting on the cart, another force acting on you. And then the two more forces are there. You, when you are trying to walk, are actually pushing the road back, the earth back. And the reaction forces, road is pushing you front. Now there are four forces here, two action and two reaction. All of them together, if you take and calculate the acceleration of each one of them, then you will actually get the resultant like this, where you are actually pushing and walking along the cart. So that is how it happens. So that's how the Newton's idea of third law and second law can be mixed together to understand things. Now, we have actually kind of covered all the Newton's laws and understood a great deal about what are his three different laws. So lastly, we are going to go and see what is the meaning of collision and how we can apply Newton's third law and second law in collision, and maybe the first law also. It is an application of all these laws. So come back and watch the next video. Thank you.